try to share this.
So the next speaker is Lee from DIOC, and he will tell us something interesting about the Brownian, about some interesting energy distribution of FRB. So please take away. Thank you.
All right. Can you see my full screen?
Yes.
Hello?
Yeah.
Yes.
It looks good, Dee.
All right, good.
Looks okay.
So this is my title, The Brownian Motion of FRB Burst in a Time-Energy Bivariate Space. That's a mouthful. And this slightly nauseating little animation, I would like to convince you by the end of the talk that those tracks, blue tracks, actually represent a fundamental characteristic of the repeating FRBs. So as Duncan has already mentioned in his excellent review, there have been many early efforts of searching for bursts, and here is one that I dig out. It's in 1977, a Scottish scientist and a US scientist tried to look for a supernova explosion within 100 megaparsec with energy of roughly 5 times 10 to the 39. So that sounds exactly like the FRB we are detecting today. And as with many such pioneering efforts, their instrumentation is not nearly adequate. And then we have this wonderful discovery, the Lorimer burst. And I was always amazed by the last sentence whenever I look at this seminal article. It reads, hundreds of similar events could occur every day. Let's keep in mind this is with a single detection that is under a lot of doubt and dispute. And then there's Thornton's discovery of 4 more. Again, at the end of that abstract, it says, study of such source population could offer an opportunity to determine the baryonic content of the universe, which was borne out by the McCourt relation. So I think both papers show amazing foresight and audacity. I think that's still driving this field today. And to actually ascertain the energy, of course, we have to know the distance, and this was finally accomplished by Xiaomi at the beginning of 2017. So with the localization of the first known repeater, we now know that within 1 millisecond, there's roughly a full year worth of solar energy, which is still unexplained. So Duncan looks happy here. His presence graced our observatory. That's, I think, is after the localization and after this field now has a confirmed cosmological origin for these bursts. So from then to now, I think the 500 aperture spherical radio telescope has become a sort of a FRB burst factory. It's a factory in the sense that it didn't manufacture any burst, but it does produce tons of papers. Particularly, we are now routinely detecting hundreds of bursts from a single source, be it 121102, 190520, 1124A, and 2022 0912A, so on and so forth. So a lot of those work are being done through this key program led by Bing Zhang and Wei Zhu. So we first, even during the commissioning period, started with, of course, 121102, the first known repeater. And we were fortunate to catch an extremely active episode of that source, and within 50 days, with about 60 hours, we detected 1,652 sources. So that moving the number of pulses from a single source into thousands. And think the next step would into tens of thousands. And the date reduction and particularly calibration largely carried out by Pei Wang from NAOC. So that's a lot of work. So now we know both from empirical experiments and theoretical estimates that we have a completeness of detection indicated by this yellow line. So above which we have a characteristic peak rate at a certain energy, which is at 4.8 times 10 to the 37, or below which the birth rate actually drops. And I also invented this little model, it's called a bimodal distribution. So at the lower energy end, the birth rate can be well described by a log normal function, which usually underlines stochastic processes. At higher energy end, it can be described by a generalized Lorentz-Cauchy function, which can be reproduced by the ratio of two independent random variables, or the probability density function of two Gaussians, basically. So that happens in, say, atomic emission when two random events that has a chance correlation. I think I shouldn't say any more in terms of its physical meaning, but this is what we can sort of win from such large data set and analysis. And FAST is also carrying out, similar to what Duncan described for GBT, a commensal survey of FRB. So while we are searching for pulsars, imaging H1, all at the same time, we also record transient data. So there's Chen-Hui Liu from NAOC first noticed this repeating burst in this single scan in different beams on May 20th, 2019. And it was finally published in the middle of last year on Nature. So far, in addition to the repeater 190520, we have also published 4 single events. And from these detections, we can backtrack out a full sky event rate. The lower limit of that is at 120,000 per day. Let's think forward. So when we have the sensitivity of SKA, is there any physical or astronomical reason to believe that we will start to see the drop of such rate? And I see none, because basically with higher sensitivity, we're still looking into a deeper and larger volume of the universe, which should still contain abundant galaxies. So we'll be looking at a full sky event rate somewhere between 1 million and 10 million per day when we get to SKA. So regardless of whether we can understand the physical mechanism of FRB, of which I'm relatively pessimistic, but such a abundant event and useful probe will remain an important frontier of astronomy for decades to come. So particularly for 190520, we have localized it with orthogonal slit position from Palomar, from Keck, and also observation from Subaru. So it has a pretty secure identification with a Meadow-Poor dwarf galaxy at redshift 0.24, and also it has a compact persistent radio source, only the second of its kind known. So this is a source that deviates severely from the regular McCord relation, and it has the highest confirmed host DM. Also, it's extremely active, and it's active in a different way. So it doesn't rival or match the peak burst rate of 121102, but it never turns off, which make it an ideal target to follow up. So with this large data set of active repeaters, we also take into account of published data from other major observatories. We notice this general uniform trend where the bursts of a repeater have nearly 100% linear polarization at higher frequency, And at a certain characteristic frequency, it will drop like a stone and goes all the way to 0. And this can be well explained by multipath scattering with a single parameter, which is so-called sigma Rm. So sigma Rm describes the local fluctuation of this integral product between magnetic field and electron density. So basically the complexity of the local plasma. And it's also curious to note that the only two known sources with compact PRS counterparts has the largest sigma Rm. So it conceivably, they may represent an early or younger evolutionary stage of repeating fast radial bursts. So this effort is continuing and largely led by my former PhD student Yifeng, now a full-time staff in Zhejiang lab, who is also trying to establish a new computational astronomy group there. So here I just list some of the already published or near publications, sort of 1905-20 B-centric papers. So there's a magnetic field reversal paper that should be coming out. And we also detect circular polarization in these active repeaters. Particularly worth noting is Stellar Oker and Jim Corda's scattering analysis. I think it's really a very useful tool. Through that, they were able to constrain the size of the scattering screen within 100 parsecs of the bursting source. And there's also theoretical models, and of course the Casey Law has this very interesting investigation of the implication of these two PRS to the whole radial source populations. So now we keep monitoring these active repeaters, particularly 1102 and 1905-20. And they stay active, which is good, but they stay active in different ways. You can see those blue dots are 12, 11, 02. So there's this conglomeration of large dots, and then it can go dormant for years. And those white dots are 1905-20, so it just stay active. So we start to accumulate, particularly in terms of sampling in cadence, from all the way from say 1 millisecond to month. So this gives us a decent dynamic range in sampling of events at different time scales. So this paper that has been submitted was led by Yunkun Zhang from NAOC. And naturally, the first thing everybody looked, and we also looked, is periodicity. And there's no short-term periodicity except for the sort of 160-day-ish long-term modulation of 12-11-02. And it's really not a periodicity because the duty cycle now is like 60%. So basically, it's an active window that occupies more than half of the full time length. So it's a sort of a modulation of some regularity. So we tried for a transform, long scargo, phase diagram, try P dot, whatever is available at the moment. And we are pretty sure that there's no short-term periodicity, say within a few tenths of seconds. It also worth noting that the burst structure can be rather complex. So this is by changing only 0.1% of the DM. And you will get different bursts. And you also get different number, different width, and different arrival time. And coupled with the fact that if you have a different telescope, or your telescope has a different system temperature at the time of the observation, you will get a very different data set, particularly within, say, tenths of milliseconds, short time scale. So we're really settled with this question of how to deal with such a rich but complex data set. So sometimes when I see paper quoting sort of 5 digits of significance DM measurement, it's not trustworthy. And of course, we all frequent this FRB theory wiki, and I think it's fair to say we haven't reached any consensus within the community. So if we do a very rough division of all the research work in astronomy, I mean, this is very objective, subjective rather. So this field of FRB that is fast growing and very new frontier is more or less contained within the first two. So we keep discovering new interesting phenomena, and we have many models or stories of how it may come about. It's either supernova or magnetar or some gravitational wave event, but we are still really far away from its physical principle. And I think the key difficulty may lie in the fact that we don't really understand pulsar emission, as Duncan also referred to. If you trace the study of magnetosphere and the plasma within, it always traces back to Goldreich and Julian in 1969. And we still don't understand how do you keep a sufficient large number of electrons while it's moving along the magnetic field line being accelerated in coherence. That's what is required to produce a strong enough or bright enough coherent pulsar emission. And little progress has been seen since early 1980s. So if we cannot really produce a natural pulsar pulse, so where do we go from here to explain something that is 15 orders of magnitude brighter? But we try. So if we try to look at the more general performance of these characteristics, we can adopt this waiting time structure. So basically we set the clock at 0 when at the first detected pulse, and then just calculate their spacing. And here I lay out a bunch of natural phenomena, so earthquake, solar flare, 2 active repeaters, and Brownian motion. And you can see that once we normalize by their average detected rate, they all look pretty random. So there's some subtle difference between Poisson, Weibull, or log normal, but they are not that significant. And the sort of short time scale, somewhere between 1 millisecond to a few tens of millisecond clustering of the 2 active repeaters, those are significant. So those represent something real to the source. And we can go one step further. So I had this epiphany last year that since we cannot predict earthquake, so it must be random, and we cannot also predict fast radio bursts, so they are also random. But there is a key difference. The difference being that we always hear about aftershock, but actually there's also pre-quake. So just take a wild guess. Are there more pre-quake, or they are more aftershock, or they are equal amount? So the intuition would tell us that they must be more aftershock, because if they are more pre-quake, the earthquake start to trending towards predictability, right? If we see a lot of small events, then we sort of build up this anticipation there must be a huge event. And in fact, we can actually quantify this by, if we have a time series and each event has its energy, and we scramble the time series and check whether there are still the same level of aftershock after certain bright event, be it earthquake or FRB. And it turns out only earthquake has that bias. So whenever you have a very strong event, you have a higher probability at getting a lot of weaker events. And active repeaters don't have that. So that means they are actually distinguishable from a random-like, it's actually chaotic-like earthquake. So we can go one step further because they are already relatively mature tools in terms of mathematical physics to study complex systems. So to characterize their randomness or stochasticity, we can use so-called Pincus index. This is actually a modified Pincus index. And to study the chaos, we can use the Lyapunov experiment. And
Sorry, 5 minutes left.
Okay, so this is almost my last slide. So stochasticity and chaos, they are all unpredictable, but they are unpredictable in different ways. So a pure random event, you cannot predict at any single instant. But chaos, if, for example, a three-body system, if you know the velocity, the position of all three bodies at a certain instant, you can perfectly predict the next instant. But the unpredictability will exponentially grow through time. So they are very sensitive to initial conditions. So the bottom line is that we put all sorts of natural phenomena we can get our hands on with real data. And on one end, we also have sine wave. It's fully predictable. It's just a function. And on the other end, we have Brownian motion, which is purely random, supposedly. So the sine wave and pulsar are very much predictable. And the fast radio bursts, the active repeaters, they are less chaotic than earthquake and solar flare, but they are more random. They are much akin to a Brownian motion. So I will just stop here, and in the form of summary is some sort of forward-looking statement. I think we just start to sort of take a crack at this sort of rich FRB data set, because in the past 10 years or 15 years for the field, we're very busy with new discoveries. And now this large data set, both in terms of number of sources and the number of bursts from a single source, really go into a regime of statistical significance. And from this sort of initial study, we think the active repeaters are boson in nature, and they differ notably from earthquakes. And the quantifiable chaoticity and the stochasticity of active repeaters tend to disfavor crossquake-like models. And if we look at how we have been studying these things conventionally, usually we look at in the energy domain, for example, the luminosity function. Then we look in the time domain, try to look for periodicity. I think it's also curious to know that except for that one quasi-periodicity, all the other systematic search for short-term periodicity of repeaters has failed. So I think that's tied into something fundamental regarding this phenomenon. But I think there's still large parameter space where we should look at this related, seemingly independent physical parameters together. And energy time are just the most obvious of them. So I will end with one statement. So let's try to supersede pulsars or supernova to the ET phase space and beyond. So thank you.
Okay, so let's take question from on-site first. Yes.
Fascinating talk. Could you go back to your first slide? You were showing us this very intriguing movie, and but you're now leaving us hanging because you didn't tell us. Okay, so could you just give us a few more words on this?
Right. Sorry, I'm a little bit rushed. So if we will each burst like a point on this diagram, so it has an arrival time and energy. Then we draw this track from the first event to the next event. Then it becomes this vector. Then we draw another vector that link into the next event. So eventually you will get this motion path that can be plotted on this energy and time space. I think now we are basically looking at a dynamic system, and there have been many tools developed to try to study such systems. I would think that's a direction that may worth some further investigation.
Okay, thank you. Next questions?
Hello, Didi. Thank you very much for very nice talk. The last figure that you showed is really impressive to me. So you mentioned the chaotic Burn-South randomness figure. And then we can see the clear defined location of FRBs from other populations. And then I have a little technical question. So how many samples do you need to plot this figure for FRBs?
So I think it's certain. I mean, I would say the empirical number will be like say 40, 50 bursts. But it's also important that they don't concentrate it sort of in one time space. For example, if you have one detection every day, that's actually not very useful because you sample at a too regular a space. So presumably you have say 50 bursts in one day, and then but you do that every day or every other day and do that for at least a few months. So to get some sampling in terms of interval.
I see. So that means first, this can be done only by first, probably. I mean, high sensitivity telescope.
So with more active repeaters, so there are only like 4 or 6 very active repeaters, but more are coming out. And both 121102 and 190520, they are perfect sources, but they are relatively far. The redshift like 0.18 and 0.4.
Yes.
For some of the recent discoveries, they're much closer. So once you move in much closer, I think a lot of other major telescopes can also do this.
Okay, thank you very much.
You're welcome.
Yeah, hi, Wei Li here. Thank you for very nice presentation. I'm trying to put together some of the things you said about the fast statistics. You mentioned 120,000 a day. Now, also putting together with the fact that you discover that some of them actually are not that distant compared to the DM. In other words, the host DMs can be very important and shouldn't just be ignored. Now, it seems to me that this is just one more step, right? So presumably, if you have an even more sensitive telescope and you're about to have 6 fast, so you'll have 6 times more.
Yeah.
Exactly, my extrapolation so far, and I wonder whether you have measured this already. The expectation in a Euclidean universe is the number of events goes as sensitivity to the minus 1.5. And that certainly Chime confirms that with a few hundred bursts. So I would say going from 1,000 to 100,000 really just means you need a 30 times bigger sensitivity, which is consistent with fast compared to Chime.
Right.
So 6 times more, I would have said you expect 20 times more bursts, so you expect about 1 million a day with fast 6. Is that correct, or is that not hold for your sample?
Yes. So 6 fast is basically SKA. Right?
Indeed, and then 6 to the 1.5 is about 15, right? So 15 times 120, you get about maybe 2 million a day. I mean, a rate at that flux level. Is that what we should expect?
So I haven't done a rigorous calculation, but my just hand-waving estimate is that once we get to SK era, we are looking at 1 million events per day.
Okay, excellent. If you have a reference, please do email me about the statistics of how to extrapolate whether this luminosity function shows any trend of deviating from this expectation. Obviously, that matters,
okay.
Right?
Yeah. Okay. Yeah, I will do a more careful job on that.
Thank you.
Okay, so this is very interesting discussion, and I believe we can talk more in the later discussion part. And let's thank Dee again. And the next speaker